So there, in this video, I'll be talking about all about how the Digitize Nodon works and all the useful things that you can do with it. So Digitize Nodon is one of the more obscure nodons available since it literally doesn't show up in any in-game tutorial or checkpoint. Its settings is almost completely empty, and while it does have a node.pj page that kind of explains what it does, it's probably still a bit too confusing for some people. So to make things easier, I've made this simple setup which visualizes exactly what's going on. So here we have the digitized nodon with an input and output, and this is its one and only setting. You can see here with this mouse, I can move the input between 0 and 1, and the output will be shown here as this green number. So the digitized nodon has only one setting, which is here, the number of stages. And in this setup, I've shown the stages here and here. So before we get too deep into things, let's first try to understand what happens if we have a digitized nodon with a most basic setting, which is 2. So in this case, if we have a number, if its decimal value is between 0 and 0.5, is going to round down that decimal value. So here between 0 and 0.5, it rounds down to 0. And if it's at least 0.5 or greater, it's going to round up to 1. And this behavior is the same regardless of what the whole number is. So in this example, you just have 0 to 1. But if the range is, say, any of these other values, like say 6 to 7, it's the same thing. 6 to 6.5, it rounds down, and 6.5 to 7, it rounds up. Now the behavior is slightly different when we go to the negative values. So for the negative values, it basically acts sort of the same, but now if the value is right in the middle, in this case negative 0.5, it's going to round down instead. You can see here from 0 to negative 0.5, it's going to round up to 0. And if it's negative 0.5 all the way to negative 1, it's going to round down. And the same for any other value. So negative 2 to negative 2.5 is going to round to negative 2, and negative 2.5 all the way to 3 rounds down to negative 3. So that's basically how the digitized value works. Whatever value that it has here, that's not the decimal, doesn't really matter. It just cares if it's positive or negative, and just plays around between this range. Now let's tackle what the setting of the digitized nodon actually means. So when we look into the setting, it says that it's the number of stages. So what exactly does that mean? Well, the number of stages is basically the number of values that the number can round to between 0 and 1. So in the most basic example with 2 stages, our 2 stages are 0 and 1. But let's say if we increase the stage to 3, now we're going to have this third stage right there in the middle. So instead of just 0 and 1, it goes from 0 to 0.5 and to 1. And here the behavior is exactly the same. It just takes whatever input you have and it rounds to the nearest value. So now with 3 stages, we now have 3 values that it can round to. So now from 0 to 0.25, is going to round down to 0. At exactly 0.25 is going to round up, because for positive numbers it always rounds up at the middle. 0.25 to 0.5 rounds to 0.5, and 0.5 to 0.75, the same thing. And once it reaches 0.75, it's going to go up to 1. And it's the same thing with you change, regardless if you change the whole numbers here. And same thing for the negative values, same behavior. Now it rounds down when it's exactly at the middle. And you can basically just follow this logic for all of the other settings that you can put. So for example, here, 7 stages. Now we have 5 extra stages here in the middle. And here I've laid out a few more values here. So the second one here is the steps. The steps basically just the stages minus 1. So basically the number of steps that you need to move from the lowest part. So like from here, for example, at 4 stages, we have 3 steps. So because we have 1, 2, and 3. And also we have here the step size, is basically the size of the interval between each of these steps. And you can easily calculate this by just getting 1 and dividing it by the number of steps. So for example, with the most basic setting, it's two stages. There's two stages. There's one step, and one divided by one is one. If there's three stages, there's two steps, and 1/2 is zero point 0.5. The next is 1/3, which is 0.33. You can see here 0.33, 0.667, and 1. Five stages is four steps, so 1/4 is 0.25, so 0.25, 0.5, and so on and so forth. Even if you go to like stage 26, now there's 25 steps, and 1/25 is 0.04 step size. So yeah, now you have this digitize nodon which rounds to the nearest 0.04. So in default GBG, the setting of stages can go from 2 all the way up to 50. So you can see here, all the way up to 50. So here's the smallest step size that you can achieve in normal GBG, which is 0.02041. It's a little bit weird since it's 50 and not 51. So the step size is 1/49, which ends up with this really ugly number. So in modded templates, it's actually possible to get digitized nodons with stage numbers greater than 50. So here, for example, in Project Janus, I have this set of different digitized nodons that are available, which have some quite useful digitized settings for different applications. Like for example, this one has a step size of 0.02. This has a step size equal to 1 frame. These are different step sizes for different powers of 2. These are for different powers of 10. Now, digitize 0 and 1, these actually don't work. I don't think the game accounted for anyone using these settings, so this is just for show. This doesn't do anything. Basically just outputs, say, 0, whatever. And also, one thing to keep in mind when using modded templates such as this, when you're using any digitized nodons with these hacked values, make sure that you don't go into their settings, because the moment that you go into their settings, it's going to reset back to 2, and there's no way of getting that back. You can see here, I can't undo. This digitize is just gone forever. Look at here, it just goes back to 2. Yeah, no way to fix that. Just make sure to, if you're using this template and using these digitized nodons, make sure you just have a copy somewhere else, just in case you accidentally open one of them, just to make sure you don't lose them forever. And it basically still works the same way as you'd expect. For example, 51 stages. We now have a step size of a very clean 0.02. If we go up to 100 stages, that's a 0.01. So this is, if you want to round your number to the nearest 0.01, this would be very useful, and so on and so forth. And that's basically how the digitized nodon works. Now let's explore a few different things that we can do with this kind of special behavior. So with just a basic digitized nodon, there's already quite a few cases where it could be useful in your games. Like the most basic setting, setting of 2 is already very useful if you just want to round to the nearest integer. You just put a digitize there and there you go. Or for example, if you want to have a specific step size for your decimal values, for example, if you set it to 11 stages, you could do something like you have an analog input and you just wanted to round to the nearest 0.1 if you don't want to deal with all of the other smaller values. You just want these 10 clean values instead. That's another use case for that. Or say if you just don't want to deal with floating point errors, you can do something like 50 stages. You still want some sort of precision with your values, but you don't want to deal with any values smaller than 0.01, so you just set it to the largest value, and yeah, it's still pretty accurate. Like the analog values here are still pretty close here, but now you're guaranteed that you're not going to deal with any floating point errors. So that's another use for the digitized nodon. So to see how the digitized nodon interacts with other nodons, here I have the same setup as before, but now in the programming screen, where I have the input here, which I can control at will, and you can see the output here. And with just the raw digitize with the stage 2 setting, you can see that it basically just rounds up or down to whichever number is closest. But this is actually not the only type of rounding that we can do with the digitize. The second type of rounding that we can do here is rounding down. And it's actually very simple to implement. Here we just take our original digitize nodon, take a constant, set it to negative 0.5, and there we go. You see that with our input here, whatever value it gets to, you see that it just rounds down to the lower integer. For example, 3.97, it rounds down to 3. When it crosses 4, it rounds down to 4, and so on. It's actually very simple. And to illustrate how this works, let's go back here. So here we have the same original setup, but now I've added this blue circle to represent our actual input. And this red circle is now our actual input minus 0.5. And that value is what's actually being sent to the input of the digitize. Here you can see what's actually happening. When our value is exactly 1, oh there, the input to our digitize is exactly 0.5. So since it's 0.5, it rounds up to 1. So the output is 1, and it's an input of 1. If it drops below 1 here, then the input of the digitize drops below 0.5 and it goes back down to 0. Now for the larger range, so when our value goes from 1 all the way up to right before it hits 2, you can see that the value of our red dot here goes from 0.5 all the way up to 1.5. And we know that 0.5 all the way up to 1.5 rounds to 1. And when our input hits 2, exactly 2, only then will our input to the digitize hit 1.5 again, and only then it's going to hit 2. And it's the same thing all the way, regardless of what value that we put here. That's basically how we do basic rounding down for the digitize. Now there's one big caveat here, which is what happens when our input is 0, when this blue dot is 0. Well, if our blue dot is 0, since the input of the digitize is now going to be negative 0.5, well, now we have a problem. Our input is 0, so if we round it down, we expect it to be 0. But because of how the digitize works, the input became negative, and now 0 gives us negative 1. As you can see here, with an input of 0, it becomes negative 1. But for any positive value that's not 0, it works perfectly. So that's one thing you need to keep in mind if you're going to use this. Make sure that you're sure that your value is always greater than 0. Now, what if you want it to also handle 0? Well, to fix that, it's actually quite easy. It's the only time where this is going to give us a wrong output is when the value is exactly 0. Well, all we need to do is to make sure that when the input is 0, that doesn't happen. And we just don't change anything else that happens with any other value. So what we can do here is actually just add a constant 1 here. So now when the input here is 0, the value here is going to be 1. And the digitize doesn't see a negative value. So from 0 all the way up to infinity, we've now ensured that the input of the digitize is always positive. Now this also means that our output here is off by 1, but we can easily remedy that by just subtracting 1 again at the output. So we just add this here, and now when the input is 0, input to digitize is still positive, it gives out 1. Then we subtract 1 again, and it gives us 0. And for literally any other positive value, the output of the digitize just becomes 1 greater than it was supposed to be, and just gets fixed back again by this constant negative 1. And we can combine these two constants since it doesn't matter how you add them. This just turns into a constant 0.5. So this is how you can do the rounding down, also accounting for zero values. So this works for any value greater than or equal to zero. Now, if you want this to also work for negative values, you can push this even further and just use a different constant here. So instead of adding 1, say we can add 100. So if we add 100, that's going to be 99.5 here, and then negative 100 here. Now, since we're increasing this by 100, well, that means values less than 0 will still work. So, for example, negative 7 still outputs negative 7, and yeah, it rounds down correctly. But when we hit negative 100, that's the point where it doesn't work anymore. So you can see if the input is negative 100, it becomes negative 101. But for values greater than negative 100, it's going to work. So if you want to deal with even bigger negative numbers, just need to make this constant even bigger. And that's basically how you do rounding down with a digitize. Now, how about rounding up? To do rounding up, we basically do something very similar. So instead of subtracting 0.5, what we can do here is just add 0.5 instead. So now here we encounter the same problem as before. When it's exactly a whole number, it does something wrong. So here in this case, it does something wrong for every positive value, including 0. But for any other value, for example, 0.39, it rounds up correctly, and when it reaches 1.13, it rounds up. So here it always rounds up, but any whole number that's greater than or equal to 0 gives us the wrong value. And only when it's like, for example, a negative number, only when it's a negative number, it works correctly. So if we want to fix this, there's two ways. So the first way is, well, the problem here is that since we're adding 0.5 here, and the tiebreaker is it always rounds up when it's 0.5, what we can do instead is, instead of sending 0.5, we can send a number that's very close to 0.5, but still less than 0.5. So for example, this number. So now, since this is technically not 0.5, it doesn't round up. And when it goes up even just a little, only then it's going to round up. So here is how we do a basic round up function in GBG. Now, in some cases, adding this constant is sometimes unacceptable. So if you recall, the number we added here is 4.9999. If we had a number smaller than this, like for example 0.00000000001, and we add it to this value, maybe it's not going to work. Instead of rounding up like we'd expect, it doesn't round up because the value doesn't cross 0.5. Now, the cases where you're going to deal with numbers that small is probably few and far between, but just in case you need to do something like that, the alternate solution that we can do here is something similar to what we did the rounding down. I said earlier, this works only when we have negative numbers. It doesn't work when there's positive numbers. So what we can do instead here is just to make sure that the input to the digitize is negative so that it always rounds down instead. So for example, we can send negative 50 here, and then add 50 back at the end. So now, when we send 0 here, what the digitize actually sees is a negative value. It sees negative 49.5, and it rounds down to negative 50. So when it goes back up, it goes to 0. And now you can see that it works for rounding up for any value right until we hit 50. So when we hit 50, it does the same wrong thing again because the input of digitize is now positive again. But any value less than 50, it now works with rounding up correctly. And if we want it to be able to deal with positive values greater than 50, we just need to make this number bigger. So that's basically how you do rounding up in GBG. We just one digitize and up to two constants. But yeah. Now the next interesting thing that we can do with the Digitize Nodon is the fact that we can actually replicate any setting of digitize using just one digitize set to 2. And how we do it is by this setup. Basically, we have our input here. We just multiply it by the number of steps that we want, set it to digitize, and then divide it by the number of steps again. So let me show you. If we want to do 4 steps, so number of steps is stages minus 1. So we want 4 steps, that's going to be 5 stages. And when we move our input here, we can see that the output of here is exactly the same. There's the same behavior regardless of what number we put here. So how does this work? So let's try to imagine what's happening here. We have our input and we're multiplying it by 4. So to make it much more intuitive as to how this setup works, let's move back to this setup where I've added this blue circle to represent the input that we're sending, and this red value is our input times 4, which is what's going inside the digitize. Now pay attention what's going on. So what's going on here is if our input is 0 to 0.25, the input to our digitize is going to be 0 to 1. And we know what happens if input of our digitize is 0 to 1. If the value is between 0 and 0.5, it's going to go down to 0. And if our value is 0.5 to 1, it's going to go up to 1. And when we move up to these other ranges, this range, when the input is 0.25 to 0.5, well, our digitized input is going to be 1 to 2. And this range is going to be 2 to 3. And this is going to be 3 to 4. So the input of our system is basically the same as this red dot here. But now the output of the digitize is just multiplied by 4. Basically, we squished the entire range by 4. So now 0 to 1 is over here. 1 to 2 is over here. 2 to 3 is over here. And 3 to 4 is over here. And the output of the digitize is just multiplied by 4. So that's why after we multiply it by 4, we just divide it by 4 again to put it back to normal. So the cool thing that we can now do with this setup that we can't do with normal digitized nodons is that we can change the steps to whatever number that we want. And we're no longer restricted to these sets of stages. So for example, if I wanted to have 50 steps, now we can do that with this setup. Now you can see the value here now rounds to the nearest 0.02, which isn't possible with the normal digitize since the maximum that we can do here is 50 stages, or in other words, 49 steps. With this, we can do any value that we want. Now, okay, we can set it to whatever steps that we want, but thinking about numbers in steps is a little bit unintuitive. So can we change it to, let's say, step size instead? I already know that step size is basically just 1 divided by the number of steps. So here we have the same setup as before, where instead of just the steps, we take 1 divided by step size and send that instead. So here with a step size of 0.25, that's the same as having a number of steps of 4. And you can see that this does exactly the same thing as before. See there, this number object is the same as that number object, or exactly the same. So now if you know your math, you know that with this configuration, with the associative property, we actually trim this a little bit more. So instead of multiplying here and dividing here, what we can do instead is divide here and multiply here by the step size instead. So this is the same as before, exactly the same, but now a little less nodons and a little simpler to understand. Now at this point, you might be seeing what we can do here. Before, with the simple digitized nodon, we can only set our number of stages between 2 and 50. Or in other words, our step size can only be between 1 and 0.02. But with this, we can easily change the step size to be whatever we want. So instead of any number between 0.02 and 1, we can change it to say 2. So now, with this setup, we can actually round to the nearest 2 or the nearest even number, which we cannot do before. I mean, change to whatever we want, let's say 10. Now we have a system that rounds the nearest 10. And see here, from 5 to 15 is going to round to 10. From 15 to 25 is going to round to 20. So it's just really simple here. Just change the step size and we have this system that can round to any step size that we want. And if you have a system where you don't need to change the step size, you just have a set step size that you want to do, we can easily shave this by changing these to maps. So here I've done the same thing here. So now instead of doing the division and multiplication by constant, we just change that to map. So here we have the division by 10 in a map form, and here we have the multiplication by 10. So now here we have the exactly same thing before. We have a system that rounds to the nearest 10. Now from this point, we can actually combine it, what we learned earlier, with the rounding. Instead of rounding to the nearest 10, what if we wanted to round down to the next 10th digit? So for example, if it's 19.5, we wanted to round down to 10 instead of going up to 20. Well, for that, we can do what we did earlier with the rounding down, which we can simply do on this digitized nodon here. So like earlier, all we did is we add a constant 0.5 here and subtract it by 1. And now we have a system where its values are still the same. It rounds down to the lower 10th digit. So here we have a system where we can basically cut off any number of digits we have at some point. For example, here we set it to 10. So this only gets the 10th digit and up. For example, here, if it's 40 something, it's always going to give us 40. And once it reaches 50, only then it's going to give us 50. And actually, since we have maps here connected to our digitize, we can actually shave this even further, removing these constants here by just simply adjusting this by 0.5. So we want the output of this map to be 0.5 more. So to do that, we just add 0.5 here. And then for this, we just need to subtract 1 to the input of the map. So to do that, we just offset this by 1. So now we have the exact same thing as before. Yeah, we can now round down to the nearest multiple using only a digitize and 2 map nodons. One more cool thing that we can do with this setup here is we can take this minus calculator, take the input here and subtract it by our output. You'll see that this new output here at the bottom is actually the remainder of our value. So right now our setting here is 10. So whatever we see here is actually the remainder of our input if we divide it by 10. So for example, let's move it up here. Right now is 12.45. So 12.45 divided by 10. The remainder of that is 2.45. And we can just 23.17 and see it only gives us 3.47. So it basically cuts off the 10th digit there, and yeah, it is very useful for applications where we want to separate digits, for example. And this is actually called a modulo, and we can change it to any value, like for example 5, and change this to 5 as well. Now this does modulo 5, and whenever it reaches 5, it just loops back to 0 and starts counting again. So I won't go too much into the mechanics of modulo and what it's used for. That's going to be a topic for a different video. But here's just a sneak peek of how it can be done using a digitized nodon. One more niche use case for the digitized nodon is for detecting ranges. So with the basic digitize set to 2, we can actually also think of it as a nodon which checks if a number is not between negative 0.5 and 0.5. So what do I mean by that? Let's say I have our input here. So if our input is between negative 0.5 and 0.5, the output of the digitize is always going to be 0. And only when it's greater than 0.5, or if it's less than negative 0.5, only then will the number or the value here be non-zero, and it will be able to activate different types of logic nodons, like textures, for example. Instead of using these constants and comparisons to check for this value, we can just use one digitized nodon to do all of that. Now, granted, this is a very rare case for you actually to do this, but we can expand it to different values. So, for example, here, let's say we want to shift our value by 1. For example, instead of from negative 0.5 to zero point 0.5, we want to check between 0.5 and 1.5. To do that, all we need to do is subtract that value here. So if we want to increase the value by 1, we just subtract the value by 1 here. So now, this digitized nodon will output 0 if the number is between 0.5 and 1.5. And if the value is less than or equal to 0.5 or greater than or equal to 1.5, only then will this value be non-zero. And we can also change the size of this range. So for example, here, instead of the negative 0.5 to 0.5 earlier, let's say we want the range, instead of being 1, we want it to be 10. So now it's negative 5 to 5. We can do the same thing here by dividing our input by that value. So we multiplied our range by 10. So here, we just need to divide our input by 10. And we can actually combine this offsetting here and the scaling here with just one map. So with one map, we can set this digitized nodon to detect basically any range that we want. So to do that, all we need to do is just grab our map here, set the output range to be negative 0.5 to 0.5, and our input range is all of the numbers that we want the digitized to output 0. For example, in this setting here, setting is negative 5 to 5. So if our input is between negative 5 and 5, we know that the output of the digitized is going to be 0. But once our input goes greater than 5 or less than negative 5, only then will the output of digitize activate to be a non-zero value. And we can change this to whatever we want. Let's say here between 55 and 238. So if we go like less than 55, it's outputting negative 1. And once we reach 55, it's going to be 0 again. And once we reach the next range, there we go, 250 something, it becomes 1 again. So here we have a new setup that can detect if a number is not within a certain range. Now, if you've seen my additive logic video, this is actually pretty similar to something we did. I mean, actually two with just one single map here. The same range here as before, from negative 5 to 5. Now, this only uses one nodon instead. So actually, in most cases, using this map as digitized solution is probably not the best solution in terms of nodon count. Probably better to use this map solution instead. However, this setup has one advantage over this other setup used in my additive logic video. So let me just set this back here. So the main difference in these two cases is actually the bounds of its range. So in this 0.0001 example, if the input is exactly on the range, what will happen is, example here, it's 4, it's 0. If it's 5, it's exactly on the range. If it's 5 or negative 5, the output will still be 0. But for this case with the map and digitize, if the input is exactly these values on the range, well here 5, it will actually turn on. And if it's negative 5, it will also turn on. So that's the only difference between these two examples. So yeah, this may cost one more nodon, but if you have a case where it's imperative that you want the output to be on at exactly the two values that you set up here, well, this might be the better solution to use instead. Now there's one more thing that I want to show you here, which is actually a bug or limitation of the Digitize Nodon. So take a look here. So here I just have a map that generates a very large constant. The constant generating right now is 8388608, and you can see that the Digitize Nodon is outputting it correctly. However, something very weird when I send it the value 8388609 instead. So when I send this value to the Digitize, for some reason, it sees 8388609, but it outputs 8388610. But we already know what the Digitize set to 2 is supposed to do. It's supposed to round to the nearest integer. So the nearest integer to this value should be itself. But for some reason, it's incrementing it by 1. So what's actually going on here? So this is actually caused by a combination of the number system that GBG uses, which is called floating point, and what I assume is a very weird implementation of rounding done by GBG. So if you're not too familiar with floating point, probably won't understand this. I won't go too much into this in this video. You can learn more about it in my input nullification video. But basically, what floating point is the number system that GBG uses, and basically for very big numbers, the precision and accuracy of numbers become very, very weird. This is the point where very, very weird things are starting to happen as well. So what I assume is happening here is the digitized nodon doesn't actually round to the nearest integer inside GBG's code. What I'm assuming that GBG is doing is that for a digitized set 2, what it's actually doing, so here's my replication of what's actually going on. What they assume that GBG does when it has a digitized set to 2 is that it first takes its input, adds 0.5, and then rounds it down. So in most cases, that should work. That should round to the nearest integer. So for example, here, let me just show you. If we have input of 1, it gives us 1. If I send it 1.5, it's going to give us 2. Yeah, it's going to give us 2. So yeah, that's another way of doing rounding to the closest integer. I'm not sure if the GBG did this because for some reason they have a round down function, but they don't have a round to the nearest integer function. So they have to do this inside the code to implement the digitized nodon. I'm not sure. But this is just what I'm observing and what I assume is happening. Now, what does this have to do with the weird case that we were seeing earlier? So let's first look at the first example, which is 8388608. So this number is actually quite special in the fact that it's now large enough where the smallest distance between numbers is now 1. So what that basically means is the game cannot represent numbers this large with decimal values anymore. The game will just always round it to the nearest integer automatically. That's how floating point works. Like when you have really, really large floating point numbers, the smaller values, the decimal values or smaller digits, start getting truncated and always rounded off. That's how all computers work. So when we add 0.5 to it, you see here, what happens is 8388608 plus 0.5 is still the same thing. And yeah, that's because it cannot represent decimal values anymore. And at this point, when it cannot represent decimal values anymore, what the game actually does is it always rounds to the nearest even number. So it doesn't do the same rounding as digitized nodons. So for example, the game will see that it's trying to make 8388608.5. So it has to choose between 608 and 609. And since the basic rule for floating point is to always round to the nearest even number. So its choice was 8 or 9. So in that case, it chooses the even number, which is 8. So here, 8388608.5 rounds to 8388608. Now, when it tries to round down 8388608, well, 83886, there's nothing to round down. It's already a whole number. So now it comes out normally. 8388628. But now let's see what happens if we change this number to 8388609. Here I just offset it by 1, 8388609. Now what happens is, well, we're doing the same thing. First we add 0.5, but now something weird happens. You have 8388609 plus 0.5 becomes 8388610. So the reason why this rounded is because this game sees 8388609.5, well, it can't represent 0.5, so it tries to round to the nearest even number. So now the nearest even number is now 10 instead of 9. So during this first step, the value already becomes 8388610. So when the game tries to round this down, now instead of like rounding down 8388609.5 down to 8388609, now all it sees is 8388610, round it down. Of course, it's going to be 8388610. So that's why this very weird thing happens for very, very large numbers. Now take note that this only happens for a very, very specific range of numbers, specifically between 8388628 all the way to like 16 million. So you're probably never gonna encounter this problem, but yeah, it's something interesting to know since I wanted to cover everything to do with digitized nodons. Another weird quirk with the digitized nodon is that there's actually a maximum value that it can output. So you've probably seen this in the infinite video already, but here we have the same outcome. The largest value that the digitized nodon can output is this value. It's a 2 to the 32. So I'm not exactly sure why. This probably has something to do with how the digitize function was implemented inside the code. Doesn't really change much with how we do it. It's just something interesting. But yeah, let's take note that the largest value that the digitize can output is this value. And just to show you, here we're trying to send a number larger than that. And yeah, it just caps out at that value. And it's the same for the negative values. If I change this to a negative output, now I'm sending negative 4 whatever. The largest negative value that they can output is negative 2 something something. So yeah, that's all I have to show with the mechanics of the digitized nodon. So to cap this video off, I just wanted to show you an example of how we can use the digitized nodon for games. Because sometimes when you look at all the numbers, all the technicalities, all the mechanics, you might not realize that, oh, this is actually useful for like very basic stuff. So here in this example, I tried to make a 2D game with different sets of rooms. So how can we use the digitized nodon to implement that? Right now we have this person nodon here. Let's try to make this game screen a little bit bigger. Set it to, let's say, 10. And yeah, it's person nodon, and let's say we want the screen to move or transition to the next room when the player nodon reaches a certain point, or let's say when it leaves the room. Let me reduce this to make it a little bit more clear. Oh yeah, how can we do that? Well, if you think about it, like if there's a lot of different rooms, you can imagine it something similar to this. Well, you can imagine that this red dot is the person nodon, and this green square is the position of the screen. Like when a person moves within this room, the screen stays in that position, and when it reaches the transition, the center of the screen moves over here. And moves on further, moves to the next room, it goes back, just follows the person, but stays in very specific points where we want the camera to stay at. So with that insight, let's try to recreate that here. So right now, our game screen size is 10. So basically what that means is we want the step size of the position of the camera to be 10 as well. So let's try to recreate the setup with the digitize with a step size of 10. So there we just take a digitize nodon, take a map and divide by our step size. Our step size is 10, so do just that. And then multiply it again. Just like this. And now let's take the position sensor. So location sensor here. And let's try to look at the output of the location sensor over here. Let's set this to y plus and show the decimal digits. And here we go. You see that here's a pair. It's over here. So basically what we want to happen is when the location of the player is between -5 all the way up to 5, you want the screen to stay here. And when the player reaches this, the player goes over 5, well then we want the camera to move 10 to the right. So here all we need to do is just connect our location sensor here and connect the output of this to the green screen. And then let's take the input of the digitize over here so we can see what's happening with digitize as well. So you can see here, when the player is about to cross 5, the input of the digitize is about to cross 0.5. So when the player crosses 5, the digitize rounds up to 1, that gets multiplied by 10, and now it moves to the next row. And now we have a very simple setup to make a 2D Mega Man style side scrolling. And we can do the same thing for the z-axis. So let me just add these extra controls for the player and do the same thing for the z-axis. So for the z-axis, the size of the game screen is, let's see, 5.62. So we want to change this to 5.62 and 5.62. And when we take the z-axis here and send this to the game screen, you can see that, yep, exactly what we want. So with only 3 nodons for each axis, we can implement this very smooth, very simple 2D top-down room type game. So this is one of the many examples that the Digitize Nodon is very important and very useful in making it much simpler to implement. And that's going to be all for this video. Thanks for watching and see you in the next one.